I'm going to be talking about getting better performance from your Clojure applications with an emphasis on numeric computation. This started for me about 2.5 years ago when I was starting to learn Clojure. And about 2 summers ago, I found out about Project Euler. And I found that this would be a great opportunity for me to practice my Clojure. And unfortunately, I found that it was a bit slow. And the big problem was boxing, which, if you're unfamiliar with what boxing is, it's the packaging of 32-bit, 64-bit primitives into Java objects, which is a very expensive operation. And the first place where I really ran into this problem was when calculating lots of prime numbers. So to review the sieve of Eratosthenes, we can mark out 0 and 1 as being non-prime, and then for each number that's not marked off, it's a prime number, and we can mark off all of its multiples. So we do that for 2, for 3, for 5, but once we get to 7, we find that we've gotten to a number that's large enough that we can just mark the rest off as prime. We can implement a way of finding primes lazily in Clojure using a lazy sequence where we have the next prime and a vector of old primes, and we just iterate through finding the next prime, which we do by just seeing if a number has prime factors. If so, then we check the next number. If not, we have a prime. Finding prime factors is simply as a matter of, well, do any of our primes divide n, where that's defined as just having a 0 remainder when you divide the two numbers. If we implement more or less the same algorithm lazily in both Java and Clojure, I found that Clojure is about 5 times slower. So what's going on here? If we were to run it through a profiler, we see that a lot of time is spent doing boxing operations. So how can we avoid that? Well, one option that we have as of Clojure 1.3 is primitive hinting for your function arguments and return values. Before 1.3, you had to have objects whenever you wanted to cross a function boundary. But this is pretty easy to do. All you do is, if you have your function, add some tags. And the result of this is a modest performance boost. Not gigantic, but the nice thing is that it's essentially free. The only price that we pay is compatibility with older versions of Clojure, but otherwise you're not making any changes at all to your algorithm, to your code. So this is something you definitely want to take advantage of. Now, there's a few problems with our algorithm. In particular, like in the sieve of Eratosthenes, we've stopped when we reach the square root of that number. Well, we can do something similar here. Likewise, instead of checking every single number to see if it's prime, we can skip all the even numbers because we know none of them are ever going to be prime. So we should be able to double our speed just from doing that. And in fact, making those two changes increases the speed of our algorithm by like an order of magnitude. And what we learn here is that no matter how much you can tweak something, if you're using the wrong algorithm, it's going to hurt you. So be sure to use the right algorithm and test it against realistic data sets. Now, if we make these algorithmic changes to both the Java and the Clojure, although they're both performing much faster, we see now that the Clojure is running about 10 times slower than Java. So what's going on? Well, the first thing that we see if we were to run this through a profiler is that a lot of things that are sequence related are taking up a lot of overhead. We can imagine if we were stepping through in the debugger through this call of has prime factor, there's an awful lot that's going on, a bunch of indirection. And I mean, that's just 20 slides. And we only just started doing the invocation. So sequences are a great abstraction. I think one of the greatest things, one of the greatest tools that we have in Clojure. But if you know what data structures you're using in your program, exploit them. You can do something very simple for here. Instead of calling conj, you just call .cons. You don't really change much here. But in code where you make heavy use of the sequence abstraction such as this, to get away from that, the code is much uglier. But is it worth it? Well, that change gives us about a 5 times improvement over what we had before, which is pretty big. And it's something you'll need to consider carefully. If you're writing library code, unless you're being explicit about what types you're expecting, you probably want to stick to sequences. But within your application, if you know the types, go ahead and exploit them. Now, if we were to see what's taking up the most overhead, we see that is related to, and I forgot what this is. Manipulating our vector. What kinds of data structures do we have that we can use? Well, vectors we all know and love. They're one of the most common data structures that we have in Clojure. And they're pretty indiscriminate with what you put in them and take out of them. And naturally, if you wanted to, when you get a value out of it, you're not going to get a primitive value. Now, there are primitive vectors which you can get using the vector of function. These primitive vectors do implement the persistent vector interface, which means that everything that you're used to doing with regular vectors, you can do with these primitive vectors. The main thing that they do differently is store everything in arrays of the primitives rather than arrays of object references. So if you try to add something that's not quite of the right type, it's going to be coerced, unless, of course, you try to do something that doesn't make any sense. The one disadvantage right now, or non-advantage it doesn't give you, is you can't get unboxed access to the contents of the vector. Now, as we saw, for example, in this morning's keynote, if you want raw speed, arrays are what you need to use. They are, of course, low-level JVM, a low-level JVM type. And you can't use most of your collection functions with them. I think you can do some sequence stuff with it, though. And the one big advantage that you get from using arrays is you can get primitive access without doing any boxing. And as we can see, in our particular code, since we're already treating the vector as an indexed thing, changing to using the arrays doesn't have a huge impact. And the result of converting over to using arrays is nearly a doubling in our performance. So that's not too bad. In conclusion, when you're thinking about which data structure you should use, if you need raw speed, you can't beat arrays. But if you want the thread safety of a persistent data structure, and if you know that you're only dealing with one type of primitive, the primitive vectors will save you a ton of heap. Now, a question might arise, now that we're no longer using a persistent data structure, is our algorithm still thread safe? And in the case of this implementation, it is because we're using a lazy seek, which provides the necessary synchronization. So if we were to see now where the overhead is, it's related to mathematics once more. And in particular, some of the safety that's given to you by Clojure. Before Clojure 1.3, if you try to do anything that overflowed, you'd be promoted up the numeric tower to a larger type. If you try to do that in Clojure 1.3 now, you get an arithmetic exception. You can still get the old behavior, by using the big int, which you can get by adding a capital N to a literal. You have always had the ability to do unchecked operations, which means using the low-level JVM op on your operands, and that will naturally overflow, and you won't get the exception. And as of Clojure 1.3, there's a compile time flag that you can turn on that will make all of your standard mathematic operators to convert to the unchecked versions. Now, doing this gives us a modest performance benefit. The main advantage to this approach, to doing this, is that you don't have to change any of your code. So if you know from your testing or whatnot that you aren't ever going to overflow out of a long, you can turn on this flag when you compile for production and get essentially a free performance benefit. Since we're on the topic of arithmetic, this can be very tricky. When you want to divide two integers, you get a rational number. And that's not something that you necessarily want. If you want to get real integral division, you have to use the quotient function. Likewise, if you're interested in getting a remainder, you may be tempted to use mod, but that provides a true modular arithmetic type division. What you really want is the remainder. Now, none of this applies if you're doing floating point mathematics, but if you're doing integer mathematics, be sure you're using the right division operator. The last bit of overhead that we see that's left in our algorithm is this get raw root. What is that? Well, if we review vars, you can create them, get their value, and as of Clojure 1.3, you cannot give them thread local bindings unless you've specifically tagged them as being dynamic. However, you can redefine them whenever you want. That's what allows us to do the REPL-driven development that we all love in Clojure. So is there a way to avoid that? Well, there is. It's called def inline. It's a mix between defin and def macro that you can convert your defin into a def inline, and what you need to do is essentially quote the body of your function as if it were a macro. And what will happen is that when it gets compiled, it'll actually be when you have a function that calls your def inline function, all that will be inlined into the caller. So with something like divides, it's not too bad. But with something like has prime factor, it gets a lot uglier. So is it worth it? Well, we only get a moderate performance boost from doing this in this particular code. So it's something you should consider carefully. Def inlining will give you that performance boost, but it also will make your code a lot harder to understand and reason about. So it's something to just consider carefully. Since we're talking about inlining, you might have constants in your program, and you might be tempted to create a var for your constants, which is nice and it makes sense. But this will incur that get raw root overhead. Luckily, in Clojure 1.3, you can mark it as a constant, and so long as its value evaluates to like a long or a double, it will be inlined in places where it's called. So essentially, it's something that's completely free, gives you no overhead, and doesn't break compatibility with older versions of Clojure. Adding all of these performance boosts together, we have overall increase of performance of the algorithm by nearly a factor of 12, which isn't too bad. In fact, we're really close to the Java performance. In fact, our Clojure code is doing a little bit more. Because we're holding on to the head of our lazy seek, we both get the synchronization from the seek and we cache the values as we go along. If we were to wrap the Java implementation in a lazy seek, we see that they're both really close. But we're doing it wrong. I can create a Clojure implementation that will run orders of magnitude faster. So what is it that I did wrong? Well, I'm using the wrong algorithm. Trial division, while it's nice and simple and easy to understand, it makes for great functional one-liners. Unfortunately, it's not the most efficient way of finding primes, and it's not really the sieve of Eratosthenes. And also, the lazy seek adds its own overhead as well, as we've seen about seeks themselves. So here's an implementation of the sieve of Eratosthenes using an array of longs as a gigantic bit set. It's very ugly, but it's fast. So consider carefully when you're implementing your algorithm of whether or not you really want to be lazy. In particular, there's a lot of algorithms that are much easier to implement in an eager fashion than a lazy fashion. There's actually there is a lazy implementation of the sieve of Eratosthenes. There's an interesting paper on it, but the constant factors on that particular algorithm are so high that it doesn't really perform much better than the non-optimized version or the non-eager version. Now, I was doing a lot of bit twiddling to create my bit set. Certainly, that's not something that is a unique need. Other people have done that before, I'm sure. And the answer is, of course. In Java, we have a bit set class that we can use. And it's essentially the same algorithm. And in fact, if we see, we can compare them side by side. And using the bit set is a little bit cleaner. And we don't really pay a performance penalty for using the bit set. In fact, for whatever reason, the Clojure bit set algorithm ran a little bit faster than the Java. I have no idea why. I'm sure it just somehow optimized better. So the lesson here is Clojure runs on the JVM, and that gives us access to many libraries out there. Other people have had to deal with linear algebra systems or collections of primitives. And so there's libraries out there that you can reuse. Don't reinvent them, especially if they've already been battle tested. So what happens if you do all of this, but you're still having some performance issues? You suspect that the compiler is adding some boxing. Well, there's a couple of tools that I found that have been really helpful in diagnosing these sorts of issues. One is a profiler, which should come as no surprise. You can use it to see where your hotspots are and kind of hone in on which methods can, or functions, can use some optimization. There's a profiler that comes at least with the Oracle JDK. It's rather Spartan. You might be better served by using some other product. Now, a profiler might be able to tell you which function might have that boxing problem, but it won't necessarily tell you where in your function you have that boxing problem. And what I found to be really helpful is a disassembler. There's one that most JDKs come with a disassembler called JavaP, and with it, if you ahead of time compile your code, you can actually see the individual JVM instructions that the Clojure compiler produces. And by examining those, you can very easily see where you have boxing, and you can experiment with adding types and whatnot to get rid of them. So use your tools. That's what they're for. So in my preparation for this talk and in general using Clojure, there's a few things that I would love to see. One is making primitive vectors, having a way to get and write primitive values without boxing. I think if we could get that, that would make those data structures much more compelling to use. Clojure 1.3 made decision to support only 64-bit arithmetic. I understand some of the trade-offs involved, but I would still love to see 32-bit arithmetic. There's a lot of things including interfaces within Clojure that expect ints. So when you have to convert between ints and longs, that's a little bit of overhead that it'd be nice to avoid. Likewise, if you don't need the full width of a long, it means you're burning up twice as much cache than you really want to. Lastly, boxing errors are hard to diagnose. It would be wonderful if, just like with reflection, there was some sort of flag that the compiler could use to let you know, hey, I'm about to do some boxing. I hope it's okay with you. And that's that. If you're interested in seeing the code examples that I use for my slides, it's available on GitHub. I don't know how I'm doing on time. I guess I have a couple of minutes for some questions. I personally don't. We saw, for example, in this morning's keynote that they're using arrays, and they have some macros that can help write arrays. There is an effort. There's a benchmarking game where different languages get together. It's on Alioth. It's hosted by Debian, where essentially a standard problem like in-body, and you have competing implementations in different languages, and they'll run them. And so there are some Clojure stuff up there, and you'll see stuff about it in the Clojure mailing list. And you can look at that code, and you'll see examples of, for example, using def inline. I'm not sure that all those examples have been updated to take advantage of all of the new stuff in 1.3, but that's certainly one place where you can look. The algorithm changes by far are the absolute most significant. I mean, just if you're using the wrong algorithm, no matter how much you tweak it, you're using the wrong algorithm. And as I mentioned, for example, there is a lazy implementation of the sieve of Eratosthenes. The Haskell implementation that I've seen used a very optimized, well, it's a functional heap, which we don't have in Clojure. And so they're able to do enough optimizations of their algorithms so that for small n, it might not be as efficient as some other things, but for large n, it starts winning out. And unfortunately, when I tried it in Clojure, the constant factors are just so huge that even though it's theoretically a better algorithm, it just didn't work out. All right, well, I think I'm about out of time, but if you like, we can meet out here or behind. All right, thank you very much.